Hello, this is Professor Glass again, and in this video we will be looking at a first neural network, which we're calling easy equation neural network. We got the idea from a TensorFlow tutorial produced by the TensorFlow people, and that's it runs in Google Colab as a Python notebook, which you should be familiar with. So we'll start by assuming that you can open up colab.research.google.com and upload the notebook and log in. Here is the uploaded notebook, Easy Equation, in Google Colab, and I'm logged in. So, as I said, we got the original from the TensorFlow authors. Okay, so this neural network is going to compute a very simple linear equation, y equals 2x plus 1. It gets trained by giving it examples of the input x value and the correct y value, and then it will learn. So some x value goes into the network, some predicted y value comes out, there's a difference, an error, and it actually goes through all of the training data, it accumulates the errors, and it tries to adjust the parameters inside the neural network so that the next time the errors will be a little bit smaller. And that's repeated until it gets somewhere close to the correct answers, we hope. And then we'll try some test data to see how well it works. So in this video, we're just going to construct the neural network so we can see how the Python code works for building a neural network. We need to start, of course, by importing. This is Python. And we can import like that. And TensorFlow is a package which is used for a lot of machine learning type of things, machine learning tasks. NumPy you know of. It's for these arrays. And inside of TensorFlow we can bring in Keras, which is the neural network package. And sometimes it can be hard, especially if you only doing neural networks, to know what's TensorFlow and what's Keras. But for our purposes, we're fine. We'll just show you what to use. Now we're going to create a very simple neural network. And I just did it. So this is a neural network which has one layer. And that layer has one neuron. And there's one input. So remember, we're trying to compute a simple function, y equals, a line. So there's one input x value. Input x value goes into the neuron, the y value comes out. So what does this code to make a neural network look like? So it's going to be a neural network object, right? And the variable called model here is going to contain our object. So Keras.sequential says it's going to be a sequential neural network, which basically means that we'll have layers one after the other. So the neural network layers are one after the other. So here is what that will look like. It's a Python list, a literal Python list, where each element of the list contains a layer. So if you take a look at the code we have up here, there is one layer in that list. So we made it's a very short list. It's got one layer in it. The layer is called dense. Dense is the most common type of neural network layer where you have neurons. So when you first learn about neural networks and you have neurons, and then all the neurons in this layer connect to all the neurons in the next layer, that's dense. So we're going to have neurons. We have only one neuron. And then we notice we had this input shape parameter here. So the question is, how many inputs come into this neuron? And so there's only one input coming into the neuron. And the other question is, it says shape. And the main idea is, if we had like a single array of 13 numbers, like a classic machine learning example is you have 13 different measurements on some lines. You have the refractive index and the amount of alcohol and things like that. And then from the 13 measurements on the bottle of wine, you get to predict which of 3 grapes produced that bottle, that wine. So there would be a single array of 13 attributes, 13 numerical attributes, a single array of 13 numbers, in which case our input shape is a one-dimensional array of numbers. But suppose we're processing images. We might have 50 pixels in the image. But when we're processing the image, it's also going to matter that it was a two-dimensional image. As we do some of the processing on the image, it's going to be useful to think of it not as a single array of 50 numbers, but as a two-dimensional array of numbers. So that's not a problem. We can organize our data as a two-dimensional array, and one picture is a 10 by 5 array, so that's our input shape. So in our case, our input shape is just 1. We just have a single number. Okay. Keras neural networks have this nice feature where you can see a summary of the network you just built. All right. It's showing that we have all the layers would be listed here. We have one layer. It's dense. All right. The output shape is ignore the 1 for understanding this, is just 1, meaning that it's a single 1 output. That's good. And it says it has 2 parameters. So what does it mean when it says 2 parameters? In particular, this layer has 2 parameters, the whole network has 2 parameters, then 2 of them are trainable. Okay? So when you build your neural network, it's helpful to do this summary thing here to see, and to see whether you got what you intended, basically. But also the number of trainable parameters is going to determine how fast the neural network trains, how complex the neural network is normally is measured by the number of trainable parameters that are inside of it. So what does this mean? Well, for a dense neural network, each input to each neuron has a single weight. Remember from when you learn neural networks, the input to each neuron had a weight in front of it. And then for the whole neuron, there's a bias value coming into the neuron. So one thing which we didn't specify is what's the equation inside of that neuron. And neurons could have rectified linear equations. They could have hyperbolic tangent. They could have some logistic function with e to the 1 minus something like that. 1 minus e to the minus something. So we never specified the equation that was in our neurons, which you can specify. But without specifying, what you get is a linear equation, just a simple line. So the output y will be a weight w times the input value x plus a bias. All right, and the training data is providing the x value and the y value, and the neural network is adjusting the weight and the bias. That's our 2 adjustable parameters. Okay. When the neural network starts, it'll put in random numbers for the weight and the bias. but then it will adjust them. When we compile the neural network, we have to specify a loss function and an optimizer function. The loss function is how we measure the error. So as part of training, a certain amount of the training data X value is put in, the Y value comes out. Delta Y is the difference between what went in and what came out. All right. Instead of just adding up those delta Y's, what we're actually going to do is we're going to square the delta Y's so that larger errors generally are going to give us, larger differences in the output are going to be giving us bigger error values with the square of the error. So the loss function takes those errors and combines them into an aggregate loss, and the bigger the error function, the more nonlinearly it's going to contribute to the loss. So essentially we're going to be tackling the largest errors harder, because the largest errors are going to be contributing disproportionately to our error function. The optimizer function is how we adjust the parameters. So we get the error, and now what to do with our adjustable parameters. And we specified stochastic gradient descent. Gradient descent basically uses the derivative of our function. So f prime is the slope of the line for the function there, and the slope at the tangent line. So if I take a small difference in the input times the slope of the tangent line, that tells me how much output will change. So what I have is, I have an error function. That tells me how much I need to change the output in the opposite direction. So if the delta Y was plus 0.5, then I need to change the output by a negative 0.5, a negative delta Y. So this derivative could tell me, what do I need to change the input by to get that output. Now, for most problems, this is a simple linear function. We could solve this very easily by hand. But most of the time you have complicated data with lots of different input values. So you have to guess which of the input values need changing by how much, okay, like that. And the functions frequently aren't just straight linear. They're almost never straight linear. So the loss function is going to help us estimate how much is going to how much change we need. The stochastic gradient descent optimizer is going to, from that input value, say, all right, how can we make adjustments? We can't adjust the input value x, but we can adjust how much we're multiplying x by, and also the bias b. And it will say, all right, I need to adjust these things. It will nudge them in a direction, adjust them by a direction, to nudge the output in the correct way to reduce the error. And then that happens many, many times. Stochastic gradient descent is a modification of gradient descent, which is useful for much more complex cases where that derivative is just not something you're really going to be able to get analytically in any meaningful way. But by doing some stochastic things, it can sort of estimate how much, by sampling the inputs and things like that, what small changes of input could probably produce the changes of output that we want. Okay, so when we compile our model, when we built our model, we never told it how it was going to evaluate the errors, and we never told it how it was going to adjust. So compiling this model produces a model with the two functions built in, the mean squared error. Okay. So again, the compile is a method on our neural network objects in much the same way that Okay, summary was a method on the neural network objects. Okay, that is the end of this video, and we will pick it up in the next.